All right, hi everyone. Um, just going to record a very quick review while I have the time. I'm going to go over the practice test that Professor Wright has provided and use that as a vehicle to do review. All right, so let's get started. First question, it's about increasing the boiling point and it had a bunch of molecules given. Remember, our approach is always to classify, to rank order them using intermolecular forces and then translate that into boiling point and melting point. And the way you do that is that as intermolecular forces increase, so do melting point and boiling point, and the enthalpy of vaporization. And what goes against intermolecular forces is vapor pressure. So in the hierarchy of intermolecular forces, remember the intermolecular forces are all nested inside one another, right? So this is all molecules which have dispersion forces. Some molecules have dipole-dipole, and fewer still have hydrogen bonding. Cool. So let's remember the nested nature of these three intermolecular forces. If you can figure out that something has hydrogen bonding, then it has all three of them. Right, so let's take a look at part A. This has O and H, so this has hydrogen bonding. This one automatically wins. This has all three. Helium, that's an element, so that only has dispersion. So that's the weakest. This is an asymmetrical molecule. Asymmetrical in terms of terminal atoms. Terminal atoms are not all the same, so that is dipole, but there is no hydrogen bonding. And N2, like helium, is elemental, so it only has dispersion. So clearly, CH3OH wins, and so CH3OH should be the highest, followed by the one that has dipole-dipole, followed by the elements. But within the elements, now you're doing head to head with dispersion, and dispersion depends on molecular weight. And the molecular weight of nitrogen is higher than helium, so this one wins overall. All right, so which of the following substances should exhibit hydrogen bonding in the liquid state? Let's see. So we want hydrogen and oxygen, nitrogen, or fluorine, so that would be this one. Next one, which of the following characteristics indicate the presence of weak intermolecular force in a liquid? Okay, so weak intermolecular force means, let's see, low melting point, low boiling point, low enthalpy vaporization, high vapor pressure. Let's see, low heat of vaporization. By the way, enthalpy of vaporization, heat of vaporization, same thing. So that would be this one. Next, which of the following species are for which of the following species are the dispersion forces strongest? Remember, it's all related to mass. Choose the biggest molecule that has the highest mass, and you're done. Which of the following can form hydrogen bonds with water molecules? The water molecule has both hydrogen and oxygen. So the minimum requirement is that the other thing has uh, just the presence of oxygen, nitrogen, or fluorine will be enough to form hydrogen bonds with water. So let's see. If there is a hydrogen attached to these guys, that's a plus, but that's not a requirement. Right? This is type 2 of hydrogen bonding. So this thing has oxygen, this thing has nitrogen, so we're done. One and oh, oh yeah, 2 and 4. Okay, so right there. Moving along, which of the following would be expected to have the highest vapor pressure at room temperature? Highest vapor pressure, which means weakest intermolecular forces. All right, so ethanol, methanol, water, acetone. If you look at the chemical formula of ethanol, Basically it's an all, right? All has the alcohol group, which is oxygen connected to a hydrogen. So this thing has all three because it has hydrogen bonding. So does methanol. It ends in all, so it has the alcohol group. So it has all three. Water also has water is H2O. It definitely has hydrogen bonding, so it has all three. Acetone, on the other hand, is a group that looks like this. You have C double bond O. There is no hydrogen attached to the oxygen. So ketones don't have hydrogen bonding in them. This is the odd one out. It has the weakest intermolecular force, so it has the highest vapor pressure. Another way of looking at the same thing, which is probably what Professor Wright wanted you to do, is high vapor pressure and low boiling point. So vapor pressure and boiling point go opposites, right? So if you want the highest vapor pressure, you're looking for the lowest boiling point, which also matches with the which of the following phase changes is endothermic? Let's just very quickly recall our changes. Solid to liquid is melting. Liquid to solid is freezing or fusion. Liquid to gas is vaporization, and gas to liquid is sublimation. Um, Solid to gas is sublimation, and the reverse is deposition. Now, if you go from a weaker state to a stronger state, so gas, uh, the other way around. Solid is like the most tightly bound state, followed by liquid, followed by gas. If you move up this ladder, you require energy. If you move down the ladder, you need energy. So, solid to liquid, that is melting, or liquid to gas, that's sublimation, or a direct jump, sublimation. All those three of those would be endothermic, so sublimation works. Question 8, the intermolecular force present in blah 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 includes which of the following? Let's take a look. Do we have oxygens, nitrogens, or fluorines? Nope, so there is no hydrogen bonding. What about dipole, dipole? Well, that makes sense because, well, you see a lot of different atoms, right? That should be enough to tell you that this has dipole, dipole. Another way to think about this is that only elements in hydrocarbons don't have dipole, dipole. So chances are this has dipole, dipole. Of course, it has dispersion. Ion dipole is definitely has 1 and 3. It doesn't have 4. Let's see if we can rule out some things here. So it doesn't have 4. This goes away. 4, 4, and it definitely has uh 3. So it's part B. Okay, so we're done. For the presence of ion dipole, you would need this, which has dipole moment, with an ion in there somewhere. So, for example, if I mix that and NaCl, then there is some ion dipole forces involved because NaCl are ions, and they can get attracted to this dipole moment molecule. Question 9: which response lists all the following pairs that are miscible liquids? So like dissolve likes, polar dissolve polar, nonpolar dissolve nonpolar. Octane, that's a hydrocarbon that's nonpolar. Water we know is polar, so that's definitely not a good mixture. Acetic acid it has an OH, so it has hydrogen bonding, so it is polar. Water is also polar, so pair 2 works. And then lastly, let's look at octane, which is nonpolar because it's a hydrocarbon, and carbon tetrachloride, same terminal atoms and a symmetric molecule actually if you draw the Lewis structure. So 3 also works, 2 and 3. Where are we with time? 121, okay. Question 10, region B on the heating curve corresponds to, let's see, solid, melting, liquid, um, evaporating, gas. So B is where you have a solid that is melting into a liquid right there. Question 11. Based on the phase diagram shown below, how will the melting point of the substance change? The pressure is increased above 1 atm. Let's see. At 1 atm, so the melting point, right? So this is solid, liquid, gas. So we want to cross territories from solid to liquid. At 1 atm, that would mean going from here to there. That happens at some temperature down here. If we increase the pressure, look what happens. The corresponding temperature for the transition rises, so the melting point will increase. It's a matter of reading the graph. Question 12. Consider a solution made from a non-volatile solute and a volatile solvent. Which of the following statements is true? Right, so we go back to our equation where P total of a solution is given by the pressures of the two components together, and each component pressure is given by I, original pressure, times the mole fraction of A, so I times the initial pressure of B times the mole fraction of B. Let's say that A in our thing is volatile and B is non-volatile. If B is non-volatile, the initial pressure of B is 0, so this term doesn't exist. So the entire pressure is just given by one of the terms, the volatile term, and it's this. Initially, this is the pressure of the volatile solvent. When you add a non-volatile solute to it, what happens is now you have to multiply it by the mole fraction. But remember, mole fraction is always a number that is less than 1. So you're now multiplying with a number that's less than 1, which makes the overall pressure go down. Just a qualitative statement would be if you mix a volatile solvent with a non-volatile solute, vapor pressure always goes down. So this is definitely incorrect. What about boiling point and freezing point? What happens when you add a solvent? Well, as we learned in colligative properties, the boiling point increases and the melting point the melting point decreases. So right there, solution must be higher than the pure solvent. So 12 is B. Right, let's look at question 13. How many do we have in total? A bunch. So we'll try and go through these as much as possible. Alright, question 13. Which of the following aqueous solutions exert the highest osmotic pressure, assuming 100% dissociation of all soluble ionic compounds? Alright, osmotic pressure equation is pi equals I times big M times R times T. So to increase the osmotic pressure, we need a high I, so something that breaks up into multiple particles, and a high M, molarity. Well, of course, if your molality is high, then your molarity is also high. So look for something that breaks up into multiple pieces and has a high molarity. Let's see. This thing breaks up, aluminum nitrate breaks up into 4 pieces, 1 aluminum and 3 nitrates. This thing breaks up into 3 pieces, 2 sodiums and a sulfate, 3 pieces, 2 pieces, and lastly, this is a covalent compound, so just 1 piece. So E is the lowest in terms of how many pieces it breaks up into, but its molarity is the highest. So now we basically need to multiply I and M and see what combination gives you the highest thing. So 4 times 0.10 gives you 0.40, 3 times 0.11 gives you 0.33, 3 times 0.15 gives you 0.45, 0.18 times 2 is 0.36, and lastly 0.35 times 1 is just 0.35, and you see that the highest multiplication occurs here. So C is the answer. For the reaction A plus 3B gives to C, the rate of disappearance of B is given by blah blah blah, which may also be expressed as. So we want to relate B and A, so let's write our thing. Rate equals reactions get negative, and you divide out the coefficient. So negative dA dt, which is equal to negative 1/3, because the coefficient of B is 3, dB dt, which equals positive 1/2 dC dt. Now we want to relate A and B, and we want to write B in terms of A. So first of all, cancel out the negatives and move the 3 over. So 3 times dA dt equals dB dt, and we are done. So it's this one. Question 15. The reaction A plus 2B product A plus 2B gives products has the rate log K equals AB cubed. If the concentration of B is doubled while that of A is unchanged, by what factor will the rate of the reaction increase? This is a question that we didn't discuss in recitation, but it's easy. A gets doubled, right? Um, and sorry, A is unchanged. B gets doubled, so you can think of B becomes twice. A just is just one time, so it's unchanged. Basically, just plug them in here and see what happens when you raise them to their respective powers. So 1 gets just raised to 1 power, B doubles, and it has a power of 3 from the rate law. So the full change is this. It's just this multiplication. 1 times 2 to the 3, which is 8, and we're done. So if A and B change by a certain factor, just input those factors and raise them to the respective power that comes from the rate law. And that will give you the factor by which the overall reaction changes by. Okay, for the following reaction, blah, 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 you have a straight line between 1 over x and times, and remember, 1 over a versus t, you have a straight line for the graph for second order reactions. So look for something that is second order, and there you have it. Specifically, the concentration is with respect to x, so the reaction is second order with respect to x. And also, the reaction rate is found to depend only on the reaction of x, which means it doesn't have any effect on y, so y shouldn't pop up in the overall rate reaction. So our candidates before were this and this because they're both second order with respect to x, but because the question says that it has no dependency on y, this can't be it. All right, next question, 17. For the overall chemical reaction shown below, which of the following statements can be rightly assumed? The reaction is third order overall, second order. So you can determine what the overall order of the reaction is. It has nothing to do with the chemical reaction itself. It's an experimentally determined law. So this is wrong. This is wrong. This also asserts that it's second order with respect to H2S, first order. Nope, don't know that. Same thing down here, don't know that. So the answer is that it cannot be determined from the information given. Okay, so Arrhenius equation is as follows. The slope of a plot of ln k versus 1 over t is equal to. Okay, so this is in terms of k. They want ln k, so let's take the ln of both sides. So that's the ln of a e to the minus a ea over rt. Logarithm of multiplication can split as addition of logarithms. So ln of e to the minus ea over rt. Ln and e cancel. So ln of k is ln of a plus, or minus rather, ea over rt, which you can write as ln a equals minus ea over r 1 over t. Okay, so y equals mx plus c, or c plus mx. There's your y, and there's your x. The question wanted the x to be 1 over t, so the slope, the corresponding slope, is negative ea over r. We're done. All right, so reactant energy is higher than product energy, so energy overall goes down. That lost energy is given off as heat, so this is an exothermic reaction. Uh, let's see, exothermic reaction, but that's not what the question is. Well, first of all, we can get this out. If the forward reaction is exothermic, then the reverse reaction must be endothermic. So this is wrong also. Um, and now we want to calculate the activation energy for the forward reaction and for the reverse reaction. So that is something we haven't discussed in recitation. So with respect to the reactant, this is how much extra you have to go for the reaction to go forward. If you're going backwards, then this now becomes your reactant, and then you need to measure the height of the hump with respect to your reactant. It's a higher hump if you're going this way. So the activation energy of the reverse reaction is higher than the activation energy of the forward reaction. All right, next. Oh shit, we didn't discuss these questions in recitation, but no problem. For the rate law, 2NO2 plus O3 gives N2O5 plus O2. The rate is given by K times NO2, NO3. Which of the following mechanisms is consistent with this rate law? Well, for one, NO2 and NO3 should be your overall reactants, right? And each of these options are two-step reactions. So if you want to get the overall reaction, you want to add them up and see what it looks like. So if we add these up, you see the N2O4 cancels here. And so what you get is 2NO2 plus O3 gives N2O5 plus O2. Okay. If you add these two up, the NO5s cancel, and you get NO2 plus O3 plus NO5 gives N2O5 plus 5 halves oxygen. Um, actually, so basically that tells you nothing new because all of these questions have the same reactants, overall reactants. Now, something to know is that the rate of the overall reaction is dependent on the rate of the slow step. Okay, so your slow step better contain NO2 and O3. See what that corresponds to right here. That's your slow step. And it has both NO2 and NO3, which finally appear in the overall rate. So that must be it. Rate of the overall equals rate of the slow step. All right, we are making good progress. And maybe I'll be more choosy with these questions. You wish to add ethylene glycol antifreeze to protect your engine to negative 17.8 degrees Celsius. The molar mass of ethylene glycol is, okay, so that's not given. And the KF is 1.86. What is the molality of ethylene glycol would you need to protect your car radiator to this temperature? That's interesting. So ethylene glycol actually is the solute here, which is added to the solvent, water. So we want to go from 0 degrees down to 0 degrees, which is the T0 or the T pure of the solvent, to a negative 17.8 degrees Celsius, which is temperature of the solution, the freezing temperature of the solution. Okay, that's easy. Delta TF equals I times KF times M. Delta TF So that's going to be a change. Oh, there's a negative involved. The change, you want to drop the temperature by 17.8 degrees Celsius, right? Final minus initial, this minus 0 equals minus I. Ethylene glycol is a molecular compound, so just 1. Kf is given 1.86. And now you want to calculate the molality, so solve for M and you're done. If the density of pure ethylene glycol is 1.1 grams per milliliter, how many moles of ethylene glycol are in 1000 milliliters? I'm just going to copy the molality answer from down here. What question is this? So this would be 21. Interesting. Okay, so maybe the answer to this question is not given down there. That's fine. So once you have the molality, let's say that the molality came out to 2, suppose. The density of pure ethylene glycol is 1.1 grams per milliliter. How many moles of ethylene glycol are in 1000 milliliters? That is a sneaky way of asking what is the molarity is to. And we have done a question like this before. So to calculate molality, you need moles and you need volume of solution. If the molality is 2, it means that you have 2 moles per 1000 or per 1 kilogram of the solvent, so 1 kilogram of water, right? So the moles can go up here, and that gives you 2. We just need to figure out what the volume of the solution is that contains 2 moles. So, let's see. Oh, okay, actually, this is an unrelated question to part A. A little tricky. This part B has nothing to do with part A. If the density of pure ethylene glycol is 1.1 grams per milliliter, how many moles of ethylene glycol are in 1000 milliliters? So that's easy. You want to convert 1000 milliliters of ethylene glycol into grams. So you don't want milliliters, you want grams. Looking at the unit conversion, that's 1.1 to 1. So that is 1100 grams. And now to get that in moles, you don't want grams, you want moles. So 1 mole is molar mass grams. Calculate the molar mass from here, put that in there, and you're done. Part C. If you have 15 liters of water in your car radiator, assume a density of 1 gram per milliliter. How many liters of pure ethylene glycol do you need to add to achieve the desired molality in Part A? Excellent question. So you've got 15 liters of water. Remember, molality denominator is mass of solvent. So if the mass of the solvent is 15 liters, that's 15 kilograms of water. That should allow us to solve for the number of moles of ethylene glycol. Knowing that the molality, supposing that it's 2, allows us to calculate that the number of moles would be 30. Using that, you can calculate what the grams of ethylene glycol are. So grams of C2H6O2 is going to be given by the 30 moles times the molar mass of ethylene glycol. That gives you the mass. And then lastly, they're asking you for liters of ethylene glycol. Use the density equals mass over volume formula to calculate your volume, which is mass over density. Whatever mass this comes out to goes here, divided by density. Density was given here of pure ethylene glycol, 1.1. and then you're done. To what temperature elevation would your car be protected in the summer? Oh, so here they want delta TB. Delta TB is given by I times KB times M. That's easy. That's 1 KB. 0.52, I think, right, for water. And then M is the molality, which we had found in part A. Supposing it's 2, it's that. That's all. Right, moving along. Uh, we've done an exact question like this in recitation, so I'm not going to go over that. Um, let me pick up one more question. This is a very easy plug and chug question. Rate always increases if you lower the activation energy. Mole fraction, pretty straightforward. What is the vapor pressure of the solution? Use this formula, P total equals PA plus PB, where each are given by I times original pressure, part of component A, times its current mole fraction, original vapor pressure of component B times mole fraction of B. Question 5. City's water supply has been poisoned with a radioactive toxin, a concentration of 0.63 milligrams per liter. Fortunately, this toxin decomposes into a safe mixture, blah, blah, blah. First order kinetics half-life is given 6.2 hours. Initial concentration is given to be 0.63. How long will it take for half of the toxin to reach a constant? Half of the toxin? What? Let's just say how long will it take for the toxin I'm gonna take out that half to reach a concentration. So your final concentration is 3.2 times 10 to the negative 5 milligrams per liter. I'm just gonna ignore that because they're the same units for A0 and A1. And so we want to figure out what T is. This is first order kinetics, so the equation is ln A over A naught equals minus KT. You have your A, you have your A naught. K is not given, but remember we can find K using half-life as follows. Do that, plug it in, and solve for T, and you're done. Alright, last question. Question 6. Use the following data to answer the questions below. Okay, so this is what I was talking about. This is a 3-reactant question. Cool. So let's write down the rate law in each case. So rate equals K, let's say A to the power of F, B to the power of N, and C to the power of, let's just say P. So you've got 8 times 10 to the negative 4 equals K. Concentration of A is 0.35 to the power of M, 0.35 to the power of N, and 0.35 to the power of P. Next, you have 3.2 times 10 to the negative 3, K, 0.70 to the power of M, 0.35 to the power of N, and 0.35 to the power of P. Thirdly, you have 6.4 times 10 to the negative 3 plus K, 0.70, 0.70, 0.70, nope, 0.35 at the end, M, N, and P. And lastly, 3.2 times 10 to the negative 3 equals K, 0.70 to the power of M, 0.35 to the power of N, and 0.70 to the power of P. All right, so you're gonna hold 2 of these constant at a time. So let's see, let's match up 2 columns. Okay, so look, 0.70, 0.70, 0.35, 0.35. So 2 and 3, you're gonna do 2 divided by 3, That's one of them. Let's do this again. So we've done A and B. Let's see B and C if we can get that. Yep, right there. 1 and 2. Let's do 1 divided by 2. And then lastly, let's do A and C. 0.70 and A and C. Yep, right there. 2 and 3. Yeah, but we already have 2 and 3. Uh, I think A and B is what we need. That's 1 and 3. 0.35. No, interesting. Um, 2 and 4. That's what gets you A and B. So in each case, you get a power, determine the three powers M and P, and then choose any of these rows of your choosing, and then calculate K using the known values of M, N, and P, and that becomes the rate law. Rate law is this thing plugged in with the values of K, M, N, and P. Overall rate of the order would be whatever M and P you found added up. What is the value of rate constant? That goes right here. And then lastly, if you were to plot ln(a) on the y-axis and time on the x-axis, what kind of graph would you expect? Well, if this whole thing came out to be first order, then remember in first order, ln of a versus t is a straight line. So if it is first order, it will be linear. If it is anything else, it's not going to be linear. And I think that covers specifically if it is first order with respect to a, because this is ln of a on the y-axis, right? So you can have your rate law like this, k, a, and let's say b is to the second power and c has third order. This will still give you a linear line for ln of a versus t because a alone is first order. However, if you have something like k, a to the power of anything other than 1, no matter what the other things are, you're going to get nonlinear behavior. Nonlinear